Today's performance, the role of Martin Connors will be played by Chris Russell. Sorry. If you want your money back.
And this is...
Okay, so Martin sends his apologies. It was just simply a question of money. He couldn't afford to make the trip.
All right, but you'll be talking about interplanetary field associations with Oljato and some
it just rolls off your tongue, 138, 175. Okay. Okay, I'm going to talk about collisions in space, and in some of the time, totally destructive collisions, which interest us for the reasons I will soon get to. But this is an example of a collision which made a lot of debris. It probably did not destroy completely the parent object, the target. But the lesson here from laboratory work is that if you hit something at 20 kilometers per second, which is typical collisional velocity at 1 AU, if you only have 1/1,000,000th of the mass of the target, then you can destroy that target completely. But most of the time that something like this makes a debris trail, and that continues on with the parent body, the one that, or the target, we might call it, for some time as that material dissipates for various ways which we will look at. Is this working? Okay, let's take a look at what debris would do if you made it at Eros. And Eros is in a region where it doesn't have many gravitational interactions. And the material that got spalled off from such a collision would simply go forward and backwards, basically, and just make a narrow stream. If we take a look now at 138, 175, which makes close encounters with the Earth and also Venus, we have 4 panels that Martin has given us today. The first one just tells us the color code. So red is the debris, the green is where the Earth is, the asteroid is a small dot, and Venus is in that light blue. And you can see in this panel that the material that has streamed out away from 138, 175 in this simulation has encountered the Earth and then gets gravitationally scattered. However, that 138, 175 itself is not hazardous to the Earth. It's going to be missing the Earth for quite some time. But after a while, then you can have quite a discontinuous debris trail. Now, that in itself isn't really threatening, but what is threatening is the fact is what happened to all this material that got scattered along the trail. And that widens the trail, and unless it gets very close to the Earth, it doesn't scatter it a long way. But it's breaking up the trail and scattering it. So you no longer know where this material is, except that we can, I'll show you in a moment, figure out where the material is along that orbit. But I lose some track of where it is perpendicular to the orbit. Now let's just talk about this collisional cascade. That the stuff that we're slamming together has masses or sizes up here. This is going down to the nanoscale in size, and this is distance. And material then eventually goes down this cascade, gets very small. Poynting Robertson will carry stuff into the sun up here, and when you get down to the nanoscale, then the radiation pressure from the sun will push outwards, and electromagnetic forces will push outward. What we did not realize until recently, when we started studying this in detail, is that these forces can be coherent, and they're not just acting on single particles. And by the fact that when we have a destructive collision that makes very small particles, that the solar wind can then not just sort of carry the particles out one by one, but in fact make a whole bundle of particles, then we can see them. And the signature that we see is in the magnetic field, and almost exclusively. There's a little plasma signature, but it's mainly in the magnetic field. And the dust is on this side, the solar wind is on this side, and there's usually a very sharp discontinuity in the components of the magnetic field. So this is the radially out from the sun, tangentially, and the normal to the ecliptic plane, basically. And this is the field magnitude. And this signature, and this is a period of about 40 minutes from there to there, this signature is very distinctive. We can find this very easily. And so we've been gone through the interplanetary records for about 40 years finding this signature. Okay, so let's go back now to Oljato, which we discovered many years ago with Pioneer Venus. And it has an orbit like this, and it's very low inclination. And when Oljato got inside the orbit of Venus, then we started seeing in this little lobe here in this diagram a large number of those signatures. And we call this the sensitive region, the object that's being pounded, the targets, when they can get inside the orbit of our spacecraft, then our spacecraft can see them. And so we looked at it over many years at different phases between where Oljato was and where our spacecraft was. And when Oljato and the spacecraft were almost lined up, but not exactly, then we saw the largest number. And when Oljato came by, when Venus, as Venus came through in here, Oljato was someplace else. So we were excited by this many years ago. Now, Oljato is an object because of its orbit. It's eccentric and goes by Mars, it goes by the Earth, and goes by Venus. It's a great one for scattering. So, as I said in the bottom line here, or we say, the debris has a fair chance of eventually experiencing gravitational scattering, and I will demonstrate that to you. We were very fortunate after we had Pioneer Venus back in the, one second. Yeah, okay, I can, it's just the lighting in here is so poorly. This period over here is where we had Pioneer Venus data. These lines are proportional to the distance of Oljato with alignment with the Pioneer Venus spacecraft and Venus when it made its pass through the inner solar system. And you can see that the distances varied from year to year. And during that period of time, we got this lobe of events where Oljato was. And then we didn't have any data for a while. But had we had data in 1999, Oljato would have come by the inner solar system when Venus was there. And so there probably was some scattering during that period of time. But we were fortunate thereafter that we didn't have data here. We could pick up data with Venus Express and do the same investigation. However, with Venus Express, we didn't see this lobe at all. And so let's see what we did see. So if I repeat this diagram where we plot versus the phase of Oljato, that we were seeing these disturbances, which we interpret as the destruction of co-orbiting debris. And it not only went down to the background level, in places it just disappeared. And if we do our simulation, then for Oljato, we see there's a lot of scattering in this particular orbit. So we think of this as indication that there were lots of co-orbitals orbiting with Oljato, and when that closest approach came, we lost a lot of them out of that orbit. Okay, so let's go to the Earth where we live, and a little bit more concerned other than an academic issue. So another asteroid that does this is 138-175. It's in an almost one-year orbit. It also has interactions with Venus and the Earth, but not Mars. And that it goes through the ecliptic plane, descending node and ascending node. It has two inside of the Earth's orbit, so it has two of these sensitive regions. And when we follow it with modern data, ACE, WIN, stereo, A and B, which have longitude spread and not just at Earth, we can get this lovely pattern here for the events, these IFEs, which are also indication of the mass that's being disrupted. And this, as Martin points out here, this asteroid will soon be an Earth co-orbital itself, but at the present time, it's not, but it's going to be. So we've done this exercise now with the modern data, and then data that we had back from 1974 to 2000. And you can see that there's the same distribution. We have no observations here back then. And the what has just happened is that there's just been a destruction of the co-orbital material in this orbit, the same at all longitudes. And when you calculate what you would expect for the destruction of this material, these objects are smaller. Oljato was a big object and it had big co-orbital debris. This particular object has smaller, much smaller, but dangerous co-orbital debris. And when we make the calculation, this is almost exactly within a factor of 3 at least, the rate that we expect this to disappear, knowing what the population of small particles are. And so, summarize. The detection of IFEs provide indirect evidence of debris streams associated with inner solar system asteroids. These streams consist of material in the hazardous size range, like 50 to 100 and down to 10 meters diameter. Based on the IFE observations, material co-orbiting with the asteroid Oljato was identified with PBO at points at Venus's orbit. And we have identification of smaller debris, but still in the hazardous range near 1 AU with 138, 175. The temporal variations are both due to scattering and just destruction, but Oljato seems to be due to the gravitational scattering, and 138, 175 is evolving through collisional destruction at present. And in both cases, it's important to be monitoring the density and location of these this material. Thank you.
We have time for one very quick question. It takes about 30 seconds.
Mike, Yeah. What this exercise does is it tells you where you should be looking with, say, radar or optically. This, this allows us to scan a large region of space. We haven't done everything, but we've focused on several targets. But this is an adjunct to a ground-based program.
We want to switch it. Continue this afterwards.